Um, Welcome everybody. I'm Riheb Mabrouk, a PhD student at the University of Monastir. Today I'm going to talk about the part of my scientific research entitled Lattice boltzmann simulation of metal foam porosity effects on phase transition phenomenon in a latent heat storage device. So this presentation is organized as follows. I will start with an introduction, then I will present the model, the physical model, then the mathematical model. I will talk about the method used to the method used for my numerical simulation, which is Lattice boltzmann method. Then I will present some results, and finally the conclusion. So the main topics of my presentation are forced convection heat transfer in the porous channel, which is saturated with fast change materials. So local thermal non-equilibrium and the entropy generation rate criteria are calculated in this during this investigation using the thermal Lattice boltzmann method. So the physical model is as seen in Figure 1, which is a rectangular open-ended channel fully filled with the porous matrix such as metal foam saturated with fast change material, which is paraffin. As seen, the top and the bottom walls are considered to be adiabatic. At the entrance of the channel, the fluid flow, which is the air, enters at constant and odd temperature at the uniform velocity to allow paraffin to start melt, and at the end, the air leaves the channel at a lower temperature, which is considered as a cold and constant temperature. Then to initiate the discharging process, the fluid flow return conversely with the same uniform velocity. Okay, so the assumptions used to simplify the mathematical model are as follows. Forced convection prevails in the channel. The fluid flow is considered to be Newtonian and incompressible. The thermophysical properties of both phases, solid and fluid, are constant, homogeneous, and isotropic, where viscous dissipation is taken into account, and local thermal non-equilibrium between the two phases is considered. So I will present the mathematical model in dimensionless form. So the variable and parameters used are as seen. Okay, so the mathematical model. The mathematical model presents the mass equation, the momentum equation, and the two energy equations, one for the solid phase and the other for the fluid phase. So, and while the initial and boundary conditions are written using the variable and parameter, using the dimensionless variable and parameters seen, as seen. So at the inlet of the channel, at the entrance of the channel, the exit and upper and lower wall. So for the upper and lower wall, the velocity is considered in the condition is the no-slip condition and the adiabatic, which are written as seen here. So the method used to do the numerical simulation is the Lattice-Boltzmann method, which consists of two field. For the dynamic field, we have one equation. However, for the thermal field, we have two energy equation, one for the solid and the other for the field with the phase. So the Lattice-Boltzmann consists of two main steps: collision and propagation. For the collision step, the particles are in the same node, and when they leaves the node to the neighbor's node, we are talking about the propagation step. Okay, so to validate our in-house code, we are a comparison is done with the results in literature, which is that of Abdedo et al. So we are represent the dimensionless local thermal non-equilibrium, and as seen from this comparison, it can be stated that our in-house code denotes satisfactory results. Okay, so the results are the results that will be presented in this presentation are as seen. The local thermal non-equilibrium parameter, which is represents in figure 4 during charging process for two Reynolds number 2000 and 4000 for three different porosities and different pore size of metal foam. Okay, so as seen for high so it's it must be noted that for local thermal equilibrium criteria, if it exceeds 5%, that means 0.05. So local thermal non-equilibrium condition must be used. However, if the LTNE parameter less than 0.05, so the local thermal equilibrium must be used. So as seen from this figure, that during charging, process, the local thermal equilibrium must be used, and as seen that for high porosity, as the pore density increase, the LTNE increase. Okay. Also, we are presented. Also, the LTNE is presented in figure 5 during discharging process for the two same Reynolds number. So, as seen here, that the local thermal non-equilibrium criterion exceeds 5%. So, local thermal non-equilibrium condition should be considered in this investigation, and as seen that during this charging process, the LTNE parameter decreases with the pore density of metal foam. Okay. Also, the entropy generation rate is depicted here in figure 5 during discharging and charging process for the two same Reynolds number, and for three different porosity and for different pore density. So it can be seen that from this figure that that as Reynolds number increase, the average entropy generation rate increases, and as seen that during charging process, also as the pore density increase, So the increases, the average entropy generation rate also increases. However, during this charging process, the entropy generation rate decreases decreases with the increase of the pore density of metal foam. And I've seen that during this charging process for the two cases, the average entropy generation value exceeds usually during charging process. So to conclude, during charging case, the decrease in the pore density for high porosity, such as 0.9, decrease the LTNE parameter, whatever Reynolds number. And during this charging case, it can be seen that the increase in pore density for low porosity decreases the LTNE parameter, whatever Reynolds number. And during melting case, that means the charging process, high porosity with low pore density should be used to reduce the system reversibility. However, small porosity with large pore density are recommended for solidifying case, that means for discharging process. And the decrease in Reynolds number reduces the reversibility of the system, whatever the porosity and the pore density. And finally, thank you for your attention.